My name is Andrew Solano, and Josh Miles and I will be presenting our project on controlling a rocket with process control. So one of the innovations that made interplanetary travel more reasonable was the invention of the ion thruster. The ion thruster uses electricity to send small amounts of mass to create thrust using very little fuel, and that electricity is generated using nuclear reactors or solar panels, so it can last a very long time for long trips of sustained flight. Aiming that thruster is one way to offset the forces that act on the rocket. So the rocket is experiencing gravitational forces from the planets around it, the sun, as well as asteroids, dark matter, and lots of things that we don't understand as well. Not only do we have forces that are very difficult to calculate, like asteroids and dark matter, but you also have problems with the rocket and just imperfections in the model where we can't perfectly predict the course of the rocket. And so our project is implementing a PID controller that will help account for those unknown forces that are common in space travel.
This all starts with the electric ion engine, where we propel our heavy metal ions out through the back. There's a cathode and an anode, and there's a very strong charge between them, and this accelerates it. And as you have that momentum going out the back, the rocket reacts by having a forward momentum. The difference between this and a chemical rocket is that the energy comes from electricity, either from solar panels or nuclear. This results in a very high specific impulse, or in other words, that the rocket is very efficient. In order to navigate through our solar system, the researchers that we referenced used various types of coordinate systems. And this is important because it's different ways of looking about how are you off course and in what direction are you going. Some of them use nonlinear programmers to find the best routes through space. Some of them use collocation, and some of them used equations like Kepler's equations that were closed form. And our method was to use Newton's equations of motion. We used F equals ma to figure out what would be the acceleration of the rocket, and the forces we got by summing up all the forces that would affect the rocket from all the planets that we knew about. And this was a good starting point to get to that PID point. Once we had summed up our forces using G times m over r squared, we were able to figure out the acceleration, then the velocity, and then the position. We did this for x and y independently, and then implemented it in a while loop. We see a little bit of that on the right. This was done numerically with iterations, so there was a dt from position to position, and this way we could speed up the simulation a little bit by going, increasing to 60 seconds instead of 1 second, and it would increase the speed a lot.
So to better understand the inputs for our rocket and how they affect it, we did a sensitivity analysis. And although the angle of the thruster is really the only input we have during the flight, changing the force of the rocket is something else we can do to see how much that affects the rocket's path. So one of the challenges that we had was finding out what to test for the dependent variable in this sensitivity analysis, because flight time and distance both imply that the rocket reaches its destination. And we wanted to be able to test all instances of the inputs, including when the rocket never makes it to the destination. So one way that we did that is we tested just the first time step of how far it traveled. And in order to make that a relative measurement that it could be used to compare other distances, we made it normalized. So we divided it by the total length of the distance between point A and point B. And so that's a dependent variable. On the right, you have in the left column the angle of the thruster, which starts at 45 degrees normally, and then it's in 10-degree increments, 2 above and 2 below. Same with the force is normally 80 newtons, but we increased it in increments of 10, 2 above and 2 below. And the dependent variable is the percentage of the trip completed in one time step. And so we assumed for this analysis that the rocket and its initial and final points are all on the same z-plane, which made the math a little bit simpler. And we believe didn't have appreciable effect on the math. We learned from this analysis that the rocket is sensitive to both force and angle, which we expected, but mostly to force. So you can see that as the angle changes of the thruster, the trip does not change significantly, at least in the first time step, but force it does. So you can see that, for example, at 80 newtons and 25 degrees, the ship is still completing less of the journey than at 100 newtons, or sorry, at 80 newtons and 45 degrees, you can see that it completes less of the trip on course at 80 newtons than it does at 100 newtons and 65 degrees, so off course. It still completes more of the trip. So we learned from this analysis that it's very important for the force to be as large as possible, even if it creates oscillations, because the trip is completed faster.
During our simulation, we were using an x and a y coordinate to, at each time point, we would predict what would happen to the rocket based on in our simulation, in our code, such as having Mercury, having Venus, having Earth, having the sun in it, and having the rocket point in a direction and seeing what would happen as a result. With a very little effect of outside sources, we have that graph on the right where it just goes in a straight line, which makes sense because as the thrust goes out the back, the rocket goes forward. Down below, we have our reason for an FOPDT model. As the rocket is affected by gravity and is pulled off course, just by simply knowing the gravities of the planets is not sufficient to put it on a course. And the FOPDT model will help to point it towards our destination. And that's something that we would fix in the next iteration.
So some of the issues that we had with our estimation and dynamic optimization results was this oscillatory behavior, where the amplitude seemed to interestingly decrease in X, but increase in Y. And what this looked like was the ship just basically overshooting and coming back and bouncing around the destination instead of actually stopping at it or reaching it. We're not entirely sure what the source of that behavior was. We have a theory that we'll discuss in the conclusion and discussion section. But ultimately, we weren't able to optimize the FOPDT model because of this oscillatory behavior. And so a PID controller has not been implemented yet. Some of the difficulties we found was that decreasing the rocket's thrust too much made it susceptible to planetary forces. So if the rocket thruster wasn't great enough, it would get pulled into the orbit of a nearby planet. But if the rocket's thrust was too great, then it would overshoot the trajectory without being able to slow down. So that was a big problem we had, as we had increased the thrust because our sensitivity analysis showed that it helped, but it made it a little bit more difficult for it to actually stop at its destination. some of our future plans that we discuss in our conclusion is to implement a braking system and ability to slow down when it reaches the destination, or at least stop the simulation when it reaches the planet, so that another set of simulations can begin to give braking protocols or parachutes or things like that, so that the rocket can slow down at the planet. The rocket was successful before we introduced the unknown forces, as we saw in the pink line graph showed that our rocket was able to go from point A to point B in a straight line and offset the forces of gravity from nearby planets. However, these unknown forces made it difficult for the rocket to respond to with the FOPDT model, which may have been bad parameters. But either way, we weren't able to get good parameters for the FOPDT model, so we weren't able to optimize the PID controller. But that would be the next step, is to isolate the cause of the oscillatory behavior, optimize the FOPDT parameters, and then implement a PID controller. And hopefully this would all begin with a braking system, although there may have been other causes for the oscillatory behavior. But overall, we do believe that the rocket is able to make it to its destination using a PID controller. Just as we better understand the system, we should be able to diagnose some of those issues.